Good morning. I'm going to work on this next section. It's the zeros of polynomial functions, and there are a couple of videos that are going to go with this. The first thing we're going to do is use a couple of theorems to find how many possible real roots, how many real zeros there are of a function, and we're just looking for possibilities, and we're going to use the rational zero theorem and Descartes' rule of signs to help us out to at least list the possibles and then go ahead and do the math to figure out what are the real roots of this function. And then the second video is going to talk about non-real roots, imaginary roots, and that's where a lot of heavy algebra is going to be taking place. Right now we're going to go ahead and use our synthetic substitution for those real roots, and if we come up with obviously a zero remainder, and then we're going to have a real root. So the first thing it says is that the rational root theorem describes how leading coefficient and constant term of a polynomial with integer coefficients determine a list of possible rational zeros. All right, and then Descartes' rule of signs says that the number of positive real roots is equal to the number of sign changes in f of x, and that the number of negative real zeros is the same as the number of sign changes in the opposite f of negative x, or less than that by an even number. And what we're going to do is we're going to go ahead and take a look at some examples. The first example is right here. I'll move it up a little bit. We have the following function. We have a function that says h of x is x cubed minus 5x squared minus 17x minus 6. We're going to determine what's happening there and what the possible factors are using these two theorems and the rule of signs. Okay, here we go. We take a look at the leading coefficient, and then we take a look at the constant term, all right? And the first thing we need to do is look at the constant term. And we take all the factors of the constant term and we put them up here, all right? So our factors are positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6, because these are the things that we can multiply to get that 6 on the end, all right? The next thing we're going to do, that's the possibles, so that's P over F is what we're really going to do. And then we're going to say, what are the factors of that leading coefficient? And luckily, we have a leading coefficient of 1. So right now, we only have 2, 4, 6, 8 possible rational zeros, but we don't know which ones actually fit into this. So we're going to start doing some guess and test. They're going to start here with negative 2, because obviously negative 2 is going to be a real zero here. They start with negative 2, so negative 2, we drop the 1. Negative 2 times 1 is negative 2. Add them together, negative 7. Negative 2 times 7 is 14. Negative 17 plus 14 is negative 3. Negative 2 times negative 3 is 6. Negative 6 plus 6 is 0. Okay? What if I wanted to start with positive 2? I'll put a positive 2 in here. And I'll do the same thing. 1, negative 5, negative 17, and negative 6. And I'm going to go through this, and if I come up with a remainder, then I don't have a factor. So negative 2 times negative 3 is negative 6. We put these together, we have negative 23. Negative 2 times negative 23 is negative 46. 6 and 46 are negative 52. So we see that 2 is not a real root, but negative 2 is a real root. Therefore, x plus 2 has to be a factor of this, and what you have left over, we might be able to factor. And if we can't factor, we're just going to go ahead and use the quadratic formula to find the rest of the real roots, and those will have our rational terms that will be roots of this function. All right? And that's what it says here. You can use the quadratic formula. All right, so we're going to use Descartes' rule of signs. Descartes' rule of signs is an interesting proposition. We're going to look down here. We knew, by the way, that this has 3 possible real roots in its function by looking at that lead term. So let's go back and let's start looking at Descartes. Descartes says every time there's a sign change, let's go ahead and look for possible positive roots. And so we take a look at this original function, and we rewrite this original function, and we look from the beginning. There's a positive, there, and then we go to a negative, and there's one sign change. You go from negative to a negative, not a sign change. All right, so we're still stuck at 1. Negative to positive, that's 2 sign changes, and positive to negative, that's 3 sign changes. So there are either 3, or then you subtract 2, or 1 positive real roots. Okay, well that's fine, but we have to check to see if there are any negative real roots as well. So let's go ahead and look for sign changes here. And what we do is we show the opposite. We just make x negative in this whole shebang, and then we start looking. All right, so this negative to the 4th power stays positive. This negative to the 3rd power is negative, so that turns out to be positive. This negative squared becomes positive, so this stays the same. And then this negative becomes negative here, so it changes that, and minus 8 stays the same. So we look here, positive to positive, no sign change. Positive to negative, there is 1 sign change, and this sign doesn't change, and this sign doesn't change. So there's only 1, okay? So using the rule of signs, this has 3 or 1 positive real zeros, or real roots, I call them, and it has 1 or 0 negative real root. And then if you graph it, you can see that there are indeed 3 positive real roots, or 3 positive real zeros. And really and truly, that's about it. I would show the graph on here. I don't have a graphing calculator handy, and I didn't put this in. I'm just going to go ahead and look at this exercise down here, and we're going to see if we can do this. All right. We know just by looking at this, this has 3 possible zeros because of this cube term. All right. And if we wanted to, we could use Descartes right away, but we're not going to use Descartes right away. I'm going to use the rational zeros here, using the constant and using the lead coefficient. So what are the possible zeros, possible factors of 20? And we have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Okay? And then our lead coefficient is 1, so we're going to say plus or minus over plus or minus 1, which is good because, you know, it helps us quite a bit that we don't have to double up on our possible real zeros here. So we have 2, 4, 6, 8, 10, 12 that we can test. All right, well, let's start at the beginning. Let's see if positive 1 is a real 0, and that would be x minus 1 when we got there, but let's go ahead and use the substitution. 1, negative 5, negative 4, and 20. All right, so we're going to drop down the 1. 1, let's see, we have negative 4. Nah, it's not going to work. Negative 4, which is negative 8. Negative 8 doesn't help us at all. We have 12 as a remainder, so we know that that doesn't work. So we're going to get rid of this, and we're going to get rid of this, and I'm going to jump up. I'm not going to use negative 1. I'm just going to start moving up the line. I'm going to use positive 2, and that would be x minus 2. So drop down the 1, you put a 2 in here. We have negative 3, negative 6, negative 10. Hey, looky, 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 we have a real 0. 2 times negative 10 is negative 20. When we add that up, we get a 0. So we know right now, even if we didn't do the math here, we know for a fact that x minus 2 is a factor, all right? So let's use what's left over, and we're going to say x squared minus 3x minus 10 is our quadratic, and we can factor this quadratic. If I'm not mistaken, this is, what do we say, x minus 5 and x plus 2, right? Because negative 5x plus 2x is negative 3x, and negative 5 times positive 2 is negative 10. So we know that these are our factors that equal 0. So our real zeros, when we finally do all of this math, are 5, 2, and negative 2. And I switched those around just because I wanted them to be in descending order. Sometimes you like to do them in ascending order, but these are our real zeros. So when you put this into the calculator and you show this graph, you're going to show that this graph twists and turns, has a little bubble, and then takes off through positive 5 there. Not a very difficult graph. See, it'll look like this. 1, 2, 1, 2, 3, 4, 5. It'll look something like this. It'll pop up here, zip down here, and zip way up here. And that's sort of what it's going to look like. And when you put it into the calculator, that's what you get. If we wanted to look at finding the possible positives and negatives, we would use Descartes' rule, and we would say, okay, well, there's a positive to a negative, so there's 1. Negative to negative, no, but negative to positive. So there's 2 possible real positive roots. And then if we change all these signs, this would be negative, this would stay the same, this would change, and that would stay the same. And so we would look, negative to negative, no, it doesn't change. Negative to positive, there is 1, and positive to positive doesn't change. So there are 2 or 0 positive real roots using Descartes' rule, and then 1 possible negative. Let's fix that up, sorry about that. 1 negative real root. And that's using Descartes and the rational zeros theorems to make sure we know what we're doing. And that's the first part of this. The next, we're going to start talking about imaginary zeros, and that's where all the real heavy-duty math comes in, and you'll love it. Thanks for watching.